And session one starts with Tom Adams. Actually starts again with Tom Adams because Tom started the last user meeting already. I think he's the first speaker doing a talk twice. Tom is from Haast Energy, a small trading firm in New Zealand. And his talk is on nodal modeling approaches of the Australian electricity market. So Tom, if you're ready, the floor is yours.
Yeah, sweet. Cool. Thanks for the intro, Lucas. Fun fact, I think 50% of the speakers are either called Tom or Lucas. There's a lot of Lucases, and I just spotted Tom there as well. Thanks for letting me go first. Obviously, New Zealand, it's a bit later in the day here, but I think the last time I did this was about 1 o'clock in the morning, so I appreciate the earlier start. So this talk is about a continuation of what I talked about last time when we were starting to use PyPSA to model price outcomes in the Australian NEM, and we've got a bit more progress now. So I'm going to talk about that. So the key thing is we want explainable prices for the week ahead or next 2 or 3 weeks. This is quite different to people doing like long-term expansion studies. So I appreciate it may not be so relevant to those people, but there are quite a lot of people in this space. So hopefully some people get some use out of this. The main thing is we want these week-ahead prices in terms of things that we understand, so we can see what it's doing and adjust it accordingly. So we want to know what the generator bids or what influence the generator bids have, and it's not short-run marginal cost, because in that kind of next month or something, like there's so many games being played that short-run marginal cost has very little to do with what people actually ask for their electricity. The weather, demand changes, and also the sort of operational plant outages and line outages, and especially line outages is where PyPSA has been invaluable so far. The general structure is we have a bunch of models that are external to PyPSA, creating bid stacks of offers from the generators, demand, wind, solar, and also the constraints. We're modeling the right-hand sides of those constraints. A lot of constraints themselves come from the market operator. And they get fed into a whole bunch of zonal models that get run to give us a probabilistic output. And there's also a nodal model, which gives us a deterministic output. I'll explain why that is so in a bit. You might notice there's a sneaky line there for stability constraints, which are a lot harder to model in PyPSA. So they're still being modeled exogenously. We'll get into a bit more detail of that in a minute. But given us, very hot topic at the moment, why are we doing all the PyPSA anyway? Why not just use machine learning? And this is basically an advert for PyPSA, so bear with me. There's an example here of 2 coal-fired power stations that were either side of a double circuit line in Australia. And then first in early May 2023, one of them closed down. So when there was 2 equally sized power stations on either side of this line, the power was pretty low between the 2 because it was balanced. But when one shut down, that line started hitting thermal overload, or lines started hitting their N-1 thermal overload limits very, very regularly. And we saw high prices as shown here. And in terms of the actual constraint that monitored these lines, you can see that as soon as Liddell shut down in the first chart, you can see the left-hand side hitting the right-hand side, and the second bit of chart shows the marginal value. So that's all kicking off. And this is just an example of an out-of-sample event. You can use a statistical model, do all your training. Things like this just will never crop up. And with more and more coal plants shutting down in Australia, lines being taken out of service that haven't been out of service in the last 20 years or so, it's very hard to get a statistical model that will capture all of these kind of things, hence PyPSA. Very quick segue into graph neural nets. We have done some experimentation with them. We can get them to model taking some lines out that we haven't taken out in the past. But if anyone's got any further with this, let me know. But I've found when you scale it up to a larger network, the convolution just washes out all of those network configuration details. So even though we did train this model to detect the impacts of lines that hadn't been out in its training data, we couldn't scale this to the size of the Australian NEM. So back to PyPSA. We train our PyPSA model. Sorry, we feed our PyPSA models a bunch of inputs. One of the most critical ones, and most commercially sensitive, so I won't go into too many details, are the predicted bid stacks of what the generators are going to offer. In Australia, there are 10 bands that they basically have a volume and a price for each band. And then there are a bunch of other models for line outages, plant outages, demand, wind, solar, etc. The main point here is these are all stochastic, and then PyPSA itself is deterministic. We're using the market dispatch functionality in PyPSA to give our market outcomes. The network itself, aggregated from a bunch of sources, but all those generators in the nodal model, then the generators are just on the nearest substation, transmission substation to them. In the zonal one, they're just aggregated into regions. And just as a very quick, what is nodal, what is zonal? New Zealand is a nodal power grid market, 260 nodes around the country, whereas Australia is actually, people call it pseudo-zonal because it's got 5 zones with 5 prices, but the generators have individual loss factors that account for the fact that if you're miles away from the city, the main regional reference node, where most of the population and demand is, then your power is potentially worth less than a generator who's right by it. But Australia is essentially zonal with a few tweaks. How that's represented in the two models, one has lots of nodes, one has only 5, as you might expect. And in terms of pros and cons of the two, the great thing about zonal is it's super fast. We can run a week at 30-minute resolution in about 3 minutes, whereas if we run a full nodal with hundreds of nodes, it takes about 15 minutes to solve a week, so a lot slower. Obviously, with the zonal, it looks a lot more like the market operators because that's what we're trying to copy. There are packages out there like NumPy that do a lot of this for you. We chose to build our own to give us more flexibility, but there are things out there. All the constraints come from the market operator. The right-hand side is statistical. It's very high level. You don't need much information. Ship out the network, just more about the constraints. Whereas if you go nodal, suddenly you need to start modeling all your Kirchhoff laws and need to know impedances of lines and a lot more detailed network information. The upside of that is that you can dig into a lot more information, a lot more granular detail, and use PyPSA to calculate your n-1 thermal constraints. So outputs from the model. Nice thing about zonal, we get this probabilistic. We can just run it hundreds of times, get lots of outputs, and get probabilities of price spikes and stuff, which is very useful. We can aggregate them into various prices and different types of generation. Down the bottom here, you can see Victoria, which sometimes has a lot of wind and sometimes has a lot of gas. It can vary quite quickly from one day to another. Whereas nodal, a lot more granular. We can actually I'm gonna do a different version of this and show you a more live version of this. So we're actually using Folium just to explore the network, and you can put your simulations in there and just look at what's being dispatched, what's being curtailed. There's a hydro that's being heavily curtailed, and look at the various line flows around the place. So there's a line outage up here causing some pretty heavy flows. The red is obviously the line outage. So finding a combination of Folium and PyPSA very useful for understanding network impacts. Back to the slides. So in summary, zonal is super fast and accurate depending on your inputs, and it's very good for getting results that look like the market operator's results, which is very useful if you're trying to predict prices in the short range. What it won't do is it won't tell you, if you don't have a constraint, then you won't be able to model it zonally. That's when you need the nodal model. If there's a new interconnect gone in or something's blown down in a storm and you don't have anything in your training data to represent that, that's when the nodal model comes out. And see its real strengths of putting in scenarios that you can model physically rather than statistically. So having both of them there, day-to-day zonal, but in the extreme situations that haven't happened in history, that's when we get a lot of good results with the nodal model, and actually really good just for understanding what's going on. Arguably, one thing about the zonal model is we don't use that much PyPSA, and some people also have models like this that they just have the solver and their inputs, and that's it. Yeah, I personally like using PyPSA because it does a lot of good data handling there with Xarray and just that sort of data management, which is why we're sticking with PyPSA. And it seems pretty fast to what it does. But yeah, if we built the Nodal one first and then went Zonal, if arguably we'd done the Zonal one first, we might have used something else. But PyPSA's been pretty good, so we're sticking with that. And on that note, hopefully that was within time. Does anyone have any questions? So first question in the chat, how close to your zonal PyPSA model comes getting actual market price distributions? Well, I'll give you a quick example in there. So here are the last 10 days forecasts for a quite recent price. And actually, this was a really tricky time. I don't think you can see my mouse, so I'm going to go like this so you can see my mouse. But you can see the black line, which is the actual prices, and these are our forecast ones. If something happened on these days around the 11th of June that wasn't well modeled, but you can see it's picking the general trend. And, with the blue lines being 10 days old, it was doing well even 10 days before the events. So it's a reasonable heads up there. So yeah, pretty good. You did actually ask about distributions. It's following the individual days quite well in terms of distribution. That's very tricky because generally it's good, but then if one day something completely unexpected happens, like something blows up, it's quite hard to get your sample size big enough to get all of those events in it. There's a hand up from Robbie.
Yeah, kia ora, Tom. In my response, how to include into energy system optimization models, to my understanding, but our graph theoretic minimum cuts could be quite useful for sort of substituting for that kind of criteria. Do you have any thoughts on that?
Yeah, so we do use cut sets mainly because the market operator does. So in terms of the statistical things where we're predicting, various of those various inputs, we do use cut sets there, like the market operator does. The n-1 itself isn't that hard because either in the zonal model, it's taken care of by the constraints the market operator give us, or in the nodal model, it's just directly in PyPSA because that's an inbuilt functionality in there. So that itself isn't super hard. But yeah, in terms of how people, how various inputs react to that, that is another more tricky problem. Does that answer your question?
That's fine. Thank you.